Good morning. I'm Cassie Davey, Senior Conference Manager for the CLEAN events, and I'd like to welcome you today to a session on storage tank emergency response. We've got a couple speakers today, and I'd like to go ahead and start with our first speaker, who is Ryan Nawrocki. He is Chief Engineer, U.S. Fire Pump Company, LLC. You can find his complete bio on the Clean Waterways portal. Ryan, welcome, and please go ahead and start your presentation.
Thank you, Cassie. I'd like to take this opportunity here to thank Clean Waterways for allowing me to present this. Give you a little bit of information on storage tank emergency responses. We've had right many responses over the last in 2018, 2019 with what was happening in the oil and gas industry. Talk a little bit about the responses and the risk management that kind of goes along with them. A lot of things have to come in play, especially when you start looking at large scale incidents, kind of like the ones that had happened in 2019. A lot of things have to come together, knowing what the calculations are going to need for what the areas are going to be involved in. Water supplies, what water supplies may be available there with it. If you're using fixed water supplies or utilizing static water supplies, can we get the water up there to it? What are the hose lays going to look like? What are the distances we're looking at? Pumping supplies. Do we even have the pumping capacity there on scene? There, we have to bring in ancillary pumps to be able to supply the needed fire flows. Delivery devices. Can we even get the delivery devices, the monitors, the trucks, the aerials even close enough to make a coordinated attack on the actual hazard of the fire and to actually get control of it. Foam handling as we get into it. I know that foam is a major question as do we use it, do we not use it, what's going to be in there. When we use it, how it's going to work. And then actually divine intervention comes into play. That's something that Dwight has been a great mentor to me over the time here, and something that he always looks at is you kind of got to sometimes you got to put in the hands of someone else to get it done. A lot of things that come into play when we start looking at this, especially once it exceeds past a single incident or into something more than what the current emergency response team, the facility, or the company that actually has it is what goes past what their capabilities are. Do they have the equipment to handle a multiple tank fire, a large dike fire, multiple incidents going on inside the one facility? When was their equipment purchased? Are his equipment sized for the hazards they have? We see a growth in the oil and gas industry and bulk storage that's out there. And are they actually prepared and ready from that side? The refinery capacities have also increased. So when you start looking at what it takes to put together, if you don't have fixed systems on the tank, and even then fixed systems can be, if they're not actuated early on, most of your fixed systems on bulk storage tanks are made for rim seal protection. Once it goes to a full surface, the likelihood of utilizing a fixed system at that point goes way down for the success rate. So if we do have to set up for a over-the-top or type 3 attack on a tank, what's going to come into play? Is the current firewater system intact enough, and is the deluge systems activated on other tanks or on other areas inside the dike area? Can we get to a static water source without having to bring in long relays? Where are we going to set up to be able to make the foam attack, to be able to have that? Can we spot the monitors close enough to the area? What's the range going to be? So a lot of moving parts have to come into play when you start looking at a storage tank, even if it's a single storage tank. Right now, what's depicted in the picture is a 9,000 GPM flow of a 239 foot diameter tank. That does not take into effect your ancillary guns that would have to be in place, or monitors to be able to do either for cooling or for backup from the standpoint in case you have a situation that's going to change where the stream reach or you can't actually get effective foam coverage across the surface of the tank. So when we get into calculations, looking at what needs to be done and knowing what it is. If you got a single tank, calculations are pretty straightforward. Knowing what the application rate, the quantity of foam, the amount of unit time, how long you're going to area that you're going to cover it on, and the density. A lot of things are actually changing. It used to be the current NFPA standard was a 0.16 application rate of gallons per minute per square foot. That has since becoming a rewrite or revision to NFPA where that's going to be going up because they were looking at what was actually going to be out there. This allows you to look basically at what the time frame is going to be, how much you're going to need, basically what the foam concentrate you're going to have to utilize for extinguishment, and the time frame. So maybe your standard is going to be at a 0.2 for the tank or a 0.24, depending on the size of the tank. That way you can look at, okay, how much am I going to have to flow? What are we going to have? What's our capacities and do it? A lot of this would hopefully come into some of your pre-planning. Some of the other areas that you also got to look at is, do we have enough firewater capacity if they have the deluge system activated, or if there's other things going on. So once we know what we're applying into or what we're dealing with, then we can actually move forward of actually setting up the system. Now, this is only identifying a single tank. You're going to take this in effect when you start adding in a potential in a dike area. If you have a spill inside there, or you have multiple tanks going in on fire, or at that point, knowing what you're going to have in those areas. The other thing is also looking at, it tells us we only need 1,520 gallons per minute of flow on this size tank. At that point, can we effectively put a gun in there that's going to, or a monitor in there that's going to reach the distance in there without going inside the tank dike area? A lot of places or entities now are saying that they're not allowing their response teams to enter the dike areas. So make sure as you're looking at what your hazard studies are and what's going to happen if you have that potential of it, how are we going to set up for it? What's going to happen at this point? So when you look at your firewater, and I kind of touched a little bit about what the firewater is going to be going, most of your firewater systems are designed for your fixed firewater systems. They have a little bit more. Do they have the pumping capacity with it? What happens when the firewater pumps are down, or potentially the firewater pumps have been used for something else if they had to use them for processed water or use them for that side? Where are the other static water sources that are available? Do you have another static water source that's close to you? Do you have it in storage tanks? Do you have it in other areas that we can pull from? If you have to set up from that, do you even have the devices and the pumps if you have to put them on scene from that side to work with an over-the-top application if your firewater system isn't fully up, or it's being tasked at that point for capacity of the other deluge systems? When you start looking, so now we've done the calculations and you look at your water supply. When we get into it, you look at this size tank, a 311 foot crude tank, 65 minutes, not including your cooling water. So we're going to have to be able to supply 18,000 gallons per minute of water foam solution for 65 minutes. That's 1.1 million gallons of water that you're going to have access to. Do we have that in there? Are you completely reliant on a fixed storage tank? Or you have a feed that comes in there, or you pulling from another raw water source? The other thing to look at when you start looking at your water supplies, where's this water going to go? Can we contain it inside the area? Is it going to be able to be controlled there? Do we have other areas that we can go from? Do we have equipment that we can use for drafting, or submersibles that we can drop in to bring water up if it's above what the capacity is of the pump for drafting there? When you also look at your delivery devices, knowing a lot of information about the monitors that you have, whether it be mounted on your apparatus or mounted on an aerial device, an elevated water stream, or trailer mounted or skid mounted. What is the reach and the distance? Where are you going to have to set this up? Have you done tests on that? Most manufacturers will supply you with a flow chart and an approximate range of that. Now that's all basically when you run the calcs on there, that's without foam. So you're going to reduce the range when you add foam to it from 5 to 15%. of the distance. Also, if you're not fully able to set up with the wind at the back, then you're also going to reduce distance as the wind changes. You deal with a large storage tank, it's going to create its own type of weather around there. So knowing what you're monitoring to do, so you can actually place it, being able to range it and get it in a place that you can do it. Also, can you even supply it with the right amount? If you're utilizing a selectable gallonage nozzle, knowing how to calculate, if I can't put 100 psi at the nozzle, how much am I going to get? Or if I'm overdoing it, because depending on how you're making your foam, this will come into a major effect of are you putting the right application of foam on there? If you're going for 1%, are you actually getting 1% of foam? Are you falling below down to 3/4 or even 0.5%? Because one, you're either over pressurizing or under pressurizing it, so your volume has changed that's coming out of that nozzle. The other thing is you're looking at is your landing zones. As you get into a tank, if you're looking at the diameter where the water stream or finished foam stream is actually going to fall inside the tank. When we look at foam runs, if you have a 230-foot diameter tank, what NFPA looks at is foam can run up to 100 feet. We kind of use a conservative rule of about 80 foot for a foam run. So basically, you have to look at once that stream finished foam lands in the tank, is it going to provide enough coverage? Or is it going to make more sense to have smaller streams, one that can be controlled and land in there and get the coverage on the tank and get a quicker extinguishment at that? Plus, you're looking at the less amount of foam that you may have to use at that point, where you may have to run longer to get your foam to seal up against the hot steel, depending on the tank that you're dealing with. Stream placement and effectivity. That's another thing. We've been talking about the range. Can you get close enough to the tank for the streams to be effective? You start looking at 2,000 gallons and a 2,000 gallon per minute stream, you may only have 220, 230 feet of reach out of that stream on a perfect day. You add foam and everything else to it, you may be looking at a sub 200 stream reach. You may have to look at larger streams to go up as you get into 4, 5, 6, 7, 8, 9,000 gallons per minute. That gives you more distance. You can be outside the tank wall. Distance is always going to be your friend, especially when you start dealing with unrefined products. You deal with crude, you deal with other products that are going to be out there. That's going to cause a potential, because you got to watch at the time frame. You don't have as much time frame to deal with crude once you see the heat wave traveling through the product. Foam logistics comes into a major play on these. So once you're ready, you got your water supply established. Now, how are we going to make foam? Where are we going to make foam? Do we even have enough of foam on site at that point to be able to handle it? So if you're dealing with the calculations on it, okay, I'm going to have to stage looking at a 311-foot diameter tank. For the 65-minute extinguishment shot, I'm going to have 35,551 gallons of foam concentrate to be able to maintain a 547 gallon per minute of foam concentrate flow into it. So how are we going to do it? Do we have totes? Are we bringing in drums of this? Are we utilizing a foam pumper to make the foam? Are we utilizing around the pump proportioning devices? Are we utilizing flow-based systems? Depending on how you're going to set up, can you even do it? Is it going to take that? 547 gallons per minute concentrate is a lot of foam to be able to handle with one single delivery device. Are we going to need multiple pumps to be able to, or multiple engines to be able to supply the foam? The other thing looking at is time frame as you bring the foam in. How long is it going to take us as we do it? Because once you start making your foam attack, you're going to have to maintain that foam blanket, or you're wasting the foam on the fire, on the incident, until you actually get extinguishment. What are you dealing with? We run the calcs, we look at it all the way as, okay, a single tank or this. Is it just a tank? Or are we dealing with a pump seal? Are we dealing with multiple tanks? Are we dealing with a dike fire? This is a prop that we use to kind of show different options there with it. What happens when the crush seal gaskets give way on a tank? If it has flame impingement from a pump seal fire and then actually lights the pump on, lights the tank on fire. What happens when you get a leak or you get a valve? that goes out on the tank. Now you're dealing with product inside the dike area. How are you going to handle those areas? If you have to spot your guns inside the dike area, now this becomes a problem. You're moving everything back further out. So do we even have the effective reach on it? Are we dealing with a refined product where we have a little bit more time? Or now are we dealing with crude oil that has a short time frame, basically once it's lit on fire before you get into a boil over or a froth over situation? So looking at a bunch of variables that come into play. We talked about the gun placement. Is the foam going to be able to travel across the burning fuel? When we start looking at how the quality of the foam is being made, the amount of foam required for your post vapor suppression. Full surface tank fires, once you get them out, that's not the end of the story. You still are going to have to maintain a foam blanket depending on what type of foam you're going to use, and what the drain time of that foam is, and watching actually what the levels are coming off the tank, whether it be LELs or it actually be the other products if you're dealing with a H2S or other contaminants on there to maintain your foam blanket and keep the vapor suppressed on there. So you may be applying foam depending on how long it takes to move the product out of the area for the cleanup. The hours, days, depending on what the size of the tank is or the size of the area is that's involved with it to actually get it mitigated where you're not having to apply. So just because you made your initial shot, you had that foam, you need to start thinking about what the time frame is going to be to bring in ancillary foam to maintain your vapor suppression. Because once the foam blanket goes away, there's the potential, because either damage to the tank, the roof is sunken, the roof's blown off, it was burned off, whether it be a geodesic in those areas, all those vapors are going up. They're going to eventually find an ignition source. When you look at your post extinguishment and vapor suppression, how long is it going to take? How many hours do you need to plan for? Ideally, early on, start talking with your oil movements from that side. How long is it going to take us to drain out the tank farm? How long is it going to take to move this product out of this tank? Are we going to be applying foam for the next 24 hours? Basically looking at what the drain time is going to be. Is it going to be around 37 minutes if it's a ARA triple F, or is it less than that? What's the product going on? Weather is going to affect all this. So you got to look at what time frame is. The other thing to look at is how much are we going to add to, if it's maybe an open top floating tank where the roof has sunk and you're applying foam on there. How much outage do we have inside the tank? Can we withstand, say it's going to take 24 hours for us to do it. Can we withstand apologize for that. Can we withstand the time frame of adding this much product to it? If we stay at a 1%, what is the amount that the tank can physically handle? In 24 hours, we're going to add almost 5 feet of water and foam solution to this tank. Do we have the outage in the tank to be able to maintain that with the area? Or are we going to have a potential now that we're going to have run product out once we get to that point before they can start draining it off? When you start looking at the internal floating roof tank, probably one of the most difficult tanks to extinguish once a fire starts if there's not a fixed system. The biggest problem that you have is, for some reason, you get product on top of that pan that starts burning, the pan sinks, or it's burning and either pan is cocked inside there. You have that vapor space between where the floating pan is and the cone roof that's on top. Only options you have is going through the eyebrow vents on the side, if you can get set up and put it on there, or waiting for the weak seam roof to fail. Then you have more potential of that, because other areas can fail in those in the tank farm or in the single tank. So a lot of things that kind of comes up, we start looking at how do you extinguish those? What are the better options that will go along with it? Foam nozzles with dry chem give you more increased reach, more dry chem capability. You get a decent foam blanket if you can apply it through the eyebrow vents, and you still have that vapor fire that's going on inside there. Then you can turn on the dry chem on there and be able to extinguish it. Most dry chem, you're going to have to get up very close, but utilizing a fire water or foam water nozzle with the dry chem shot inside the water cone can allow us to carry in upwards of 150, 160 feet now, and be effective from those areas. We're looking at areas to be able to go out further, but this gives you another tool to catch it earlier on and be able to control this. Because what will happen is if you just are able to apply foam to the tank, you still have that fire burning in the vapor space. Until you put that fire out, it's going to burn your foam blanket off, and then you're going to be back to a full surface fire with a internal floater. Thanks for the time and ability to present with you guys and bring some information from some of the other incidents that went on, just some of the tools that worked out for us.
Hey, Ryan, thanks so much for that. We're here in Houston, and I look at those pictures of fires, and it's hot enough here without those fires, so I don't know how you guys would even want to have that job, but thank you. Hey, I have a few questions for you. Looking at your presentation, the first one that I was wondering about is what's critical in establishing adequate water supply for a storage tank with top over application?
Okay, well, that's a very good question, Cassie. So we're looking at once you start making an application on, say, like a single tank, if your water supply is not adequate to be able to reach the gallons per minute that you need to flow into that area, or you have an interruption once you start making your foam application, you're going to have that foam you may have shot initially will get burned up if you don't have extinguishment at that point. So that can cause you to use more foam than what's needed, or it can cause the fire to get out of control again, and then you're starting back from scratch.
Okay, well, then that leads me to another question that's kind of connected to that is what do you control and establish, how do you control and establish proportioning rates when applying?
Well, depending on the size of the tank and depending on what your application is going to be, whether it be a spill fire, a storage tank, a dike area, you got to look at what the calculation, what the application density is going to be needed for it. Depending on the type of foam that you're using also comes into play, because now you got to look, okay, can I proportion it at 1%? How much quantity am I going to need? Or do I have a 3% or do I have a 6% foam that I'm dealing with now? Can I even be effective at the proportioning? Do I have enough around the pump proportioners? Do I have enough jet pumps that I can do with it? Or do I have other systems that I can bring in place for flow-based systems where it may not matter up to a point? There is a limited size. As you get into larger storage tanks, it's going to be very difficult to maintain that proportioning. If you're under the 1%, depending or under the 3% or whatever the foam was designed for, that can completely affect how the foam works and what the quality of the foam is, and it may not be as successful on the extinguishment.
So I know fires vary greatly. So you've talked about foam in different ways. What other kind of industrial firefighting tools are used for extinguishment?
Well, that was one of the things I talked a little bit about in the presentation was the dry chem. Most storage tank fires and incidents that have happened, you have a three-dimensional or you have a pressure fire that's dealing with it, whether it be from the failed gaskets on the tanks, crush seal gaskets, other areas that creates a atomized or a pressure liquid that's on fire. So the dry chem comes into play. We're trying to look at utilizing that. It takes a practice of utilizing dry chem, knowing how to use it to put it out. When you look at what the industry is going on and what we teach, and most of the time you're able to go in and capture a fire and isolate it. Well, in certain incidents that you deal with that have been dealt with, there wasn't an option to be able to go in and isolate. So that brings in the dry chem as an option, and having the nozzles and the delivery devices to apply that correctly and knowing the techniques to do it.
Okay. Well, Ryan, thank you very much for your presentation today.
Thank you.
I'd like to go ahead and welcome our next speaker, who is Stephen Pepper, Director of Crisis Management, Phillips 66. You can find his full bio on the replay portal as well. Stephen, thank you for being with us here this morning. Go ahead and start your presentation.
Thanks, Cassie. So I'm going to talk about storage tank emergencies from an industry operator perspective. Just as a disclaimer, all of the views and points that I make are mine alone and don't necessarily reflect the views of any specific company or industry group. Go ahead, Carrie. So we're going to talk about storage tank emergency management in three buckets. So we'll visit a little bit on prevention, preparedness, and then take a deeper dive into response. Go ahead. So prevention. When we talk about prevention of storage tank emergencies, it starts with the construction standards of building the storage tank. You know, how do you design it? How do you build it? What different systems do you put in place? Process safety management principles. You know, we want to analyze the hazards and manage risk. We want to have good mechanical integrity programs that maintain the systems that we design into our storage tanks and into our bulk storage facilities. We want to have good change management. So as we're making changes in facilities or making changes to tanks, that we think through the risks and hazards and mitigate those in the change management process. And then stop work authority. Many times we see storage tank emergencies are related to human interaction with the systems. And sometimes our employees or contractors, vendors, don't feel like they have the authority to stop work and mitigate those things before they happen. So stop work authority is a big piece of the human side for preventing storage tank emergencies. Go ahead, Carrie. So here's an example cause diagram, and I pulled this out of the last fire 2015 version of risk reduction options. So Last Fire is an industry consortium of about 22 different companies from around the world that work together on large atmospheric storage tank emergencies. And so one of the things when we think of prevention is really understanding what threats are present, making sure that we have barriers to address those threats. And if a barrier fails and we have a threat present, we could have flammable material that's out in the environment. And then on the other side of the cause diagram is ignition source. And so if we have a threat present, like a thunderstorm or hot work, and we have barriers that fail, like our lightning protection or our permit programs, and those two come together, then we could have a fire. So understanding the threats, the barriers, and making sure that we have good barriers for all the threats that are present help us to prevent storage tank emergencies. Go ahead, Carrie. So incident probability, how can we reduce incident probability? And one of the primary ways is good operating practices. So good storage tank operators have good programs around their operating procedures, their maintenance procedures, their design and construction standards, all of those things that go into our practice of building and maintaining and operating a bulk storage facility. We want to avoid loss of containment. So whether that's tank gauging, sampling, our level alarms, our tank inspection programs, all of those things work together to make sure that the flammable and combustible liquids that we store in storage tanks stay in the storage tank and not get out into the environment. And then we want to avoid ignition sources. So we want to have all of those things, all of those barriers in place that reduce the likelihood of having an ignition source, even if we do get loss of containment. On the other side, how do we reduce the consequence? So if we have an initiating fire event, how do we keep it at the smallest level and the smallest consequence possible? So incident detection, how do we identify loss of containment? How do we have fire and gas detection? All of those things are built into the program or into the facility. Passive fire protection measures, active fire protection, whether it's foam systems, water systems, gas systems, Incident response measures. So how do we have a response team on site? Do we depend on our local fire department? Do we have emergency response vendors like Ryan and his company that presented before? And then emergency planning. Have we done all of those calculations that Ryan talked about, and we know what we would need in the case of an emergency? And if the emergency is small, we are able to address it and we are able to prevent escalation. But if we have a large incident, we know what that looks like as well, and we've planned for all of the parts and pieces to be able to address it and reduce that consequence. Go ahead, Carrie. So when we talk about fire protection design, as an operator of large atmospheric storage tanks, passive fire protection is built in. Those are the things that we build in that you don't have to go do. So we talk about tank spacing. The greater the spacing between tanks, the less likely for escalation to involve multiple tanks. The less spacing, the more likely that we have to have that escalation. Roof design. So one of the things that we looked at in last fire, probably 10 or 15 years ago, was really looking at the design of roofs on tanks. And one of the things that somebody had an epiphanal moment was, if we have a roof that would never sink or burn up in a fire, the largest fire we would have would be a rim seal fire. Kind of let that sink in for a minute. So the more money we put into roof design offsets the emergency response money we have to put if the roof is burned away or the roof sinks or the roof goes away. So one of the things for passive fire protection is really in that design and understanding what the threats are and designing those threats out. Lightning, stray spark control. The largest contributor to ignition sources and fires in bulk storage facilities is lightning. Another piece is stray sparks. So whether that is grounding and bonding issues or welding or controlling all of those different things, static control, making sure that the roof moves freely up and down with the liquid level. We need to make sure we control all of those things where we don't have stray sparks in other parts of the system. And then overfill protection. We don't want to get hydrocarbons or flammable and combustible liquids outside of the container. And so the more that we can do to ensure we have redundancy in overfill protection, the less likely we are to have that hazardous atmosphere outside of the tank mixed with oxygen to complete at least two parts of the fire triangle. And then active fire protection, fixed systems, semi-fixed systems, mobile systems. Ryan talked about those a little bit, and I'll talk a little more about them in the response. Go ahead, Carrie. So preparedness, and I'm just going to spend a little bit of time here. Preparedness bucket is all about contingency planning. It's engagement of our stakeholders. Do you sponsor workshops with your local LEPCs and first responder organizations? I put in parentheses, Harris County Firefighters Association. Our company, we put on a workshop every year with the Harris County Firefighters Association Field Day to talk about bulk storage emergencies in a stakeholder engagement workshop. We also give grant opportunities for local fire departments in communities where we operate to send their firefighters to corporate fire school with us and learn more about storage tank emergencies, flammable and combustible liquids and gases, and how to deal with those. Go to your area committee meetings and regional response team meetings. Spend time with your regulators, whether it's the drills and exercises from the Oil Pollution Act, whether it's OSHA, risk management plans. In Texas, the Railroad Commission governs caverns, and Texas General Land Office for the coastal zone of oil spills. So all of those things help us be prepared in the event that we were to have an emergency. And then participation in industry research and organizations. We have members of our company and members of industry that sit on many different NFPA technical committees, API technical committees, American Fuels and Petrochemical Manufacturers technical committees, Last Fire, Global Benchmarking Group, the Petroleum Environmental Research Foundation, and then the Joint Oil Industry Firefighters Association, that is another global organization. Go ahead, Carrie. So response is really after the emergency occurs. How do we train for it? How do we cascade employee response teams in? What support contractors do we have in place? And then fire protection systems and equipment. Carrie? So we'll deep dive into fire protection systems and equipment. And some of this is going to be a little bit of a build or companion to what Ryan talked about. Go ahead. So storage tank construction. And what we're talking about in this session is all about large atmospheric storage tanks. So they store material that stays a liquid at normal atmospheric pressure and temperature. So the flat bottom and the flat roof are there because there's no internal pressure that you need a domed roof. There's several different types, and Ryan talked about some of them. External floating roofs or open top floating roofs. There's many different ways to talk about that. So the shell of the tank holds the product, and the roof floats up and down on the product as product is moved in and out of the tank. A build on the external floating roof tank is a domed floating roof tank. So you've got that external floating roof with a pretty beefy roof that moves up and down, and then you put a geodesic dome on top to help with reduce emissions that come through the seal area. Internal floating roofs and cone roof tanks. So an internal floating roof looks like a cone roof tank with a thinner floating roof that keeps the emissions down inside the tank. And if the seals are in good working order and the roof is in good working order, there's really not a flammable mixture above that internal floating roof as it moves up and down the tank. And you can check that at the eyebrow vents to see tank integrity or seal integrity. The cone roof, there's no roof, so all of the vapor space above the liquid is flammable or combustible vapors into that area. And the picture below is a picture that's all around the country of infield tankage. This is what our local fire departments respond to more often with those smaller infield battery tanks, and most of them are cone roof tanks. Go ahead, Carrie. So what kind of fires, what kind of emergencies can we have with the large atmospheric storage tank? So rim seal fires are the most common, and that's when the rim seal around the roof has a failure or a leak and some ignition source, and it just burns in that annular space between the roof and the shell of the tank. It could have a product spill on the roof that catches fire. If the roof either sinks or is removed and the whole full surface of that liquid burns, or we could have a fire in the bund area around the tank, or we could have a combination of multiples of those. Go ahead, Carrie. So if we have a fire and we need to suppress the fire, we need to deliver some kind of suppression media. Ryan talked about foam systems, he talked about dry chemical systems, and he talked about all these different pieces that make that up, whether it's water supply or foam concentrate supply, how we move the fluids from supply points to delivery, how do we mix the stuff together, and then how do we put the juice onto the surface of the liquid. Go ahead, Carrie. So water supply, Ryan talked about, whether we pull it from a tank, or I call it infinite volumes. We're pulling it out of a river or ocean or some very large body of water, or tanker shuttling. So if you looked at those little infield tanks, there's probably not a hydrant anywhere close to that. And to get water to do those kinds of firefighting may require tanker shuttle operations. If you have a large atmospheric storage tank or even a small atmospheric storage tank and tanker shuttling is your operation, you really need to understand what that looks like and plan for what happens if it escalates. Where are you going to get water for escalation? Go ahead, Carrie. Foam supply, Ryan talked about this pretty well. Whether you're using 5-gallon buckets, 55-gallon drums, totes, big 18-wheeler transport trailers, or foam tenders that may have 3,000 to 5,000 gallons of foam concentrate in them. Somehow you're going to have to put all of your foam concentrate supply into a location that you can easily get it to proportioning and to the delivery device. Many times that's not really well thought out of how do I work the logistics of foam supply. And until you really look at what does that 18,000 gallons of foam concentrate that Ryan talked about, what does that look like in a field to be able to deliver to the delivery device? It can really change your perspective of where you put your foam supply and how you work that. Go ahead, Carrie. Fluid transfer. So do we have the pumps, whether they're stationary pumps or portable pumps, the piping systems, our hose, and our appurtenances and appliances? Ryan talked, about equipment that we, may have had that's 10, 15, 50 years old in different facilities that were built a long time ago. One of the things as storage tanks have grown in size, hydrants need to grow in size as well. So you can see in that bottom left-hand corner, this is what a modern water supply hydrant looks like in a bulk storage facility with large tanks. How can you get the amount of water that Ryan was talking about to the equipment and to the delivery device to be able to put it on? And small municipal hydrants that are putting out 900 to 1,500 gallons a minute per hydrant, it takes a whole lot of hydrants to get that water that you need. So you really need to look at your water supply systems around your facilities. Go ahead. Hose links. So that logistical challenge, if you're using 12-inch hose, it takes a whole lot less hoses to move the 18,000 gallons a minute. And so this is a hose chart for an 18,000 gallon a minute application, 1,500 feet, and maintaining approximately equal pressure drop across the hoses. So if we're using 2.5-inch hose, which was popular when I first started into the emergency response business, we would need 135,000 feet of 2.5-inch hose, and we'd have to lay 90 2.5-inch hose lays, 1,500 feet, to get that amount of water to put it onto the tank, versus 3 12-inch hoses, so 4,500 feet of 12-inch hose. Go ahead, Carrie. Mixing the fluids. So whether you're using jet pumps or bypass adductors, or you're using your balanced pressure around the pump systems on your engines, You have to have the appropriate way to mix the foam concentrate with the water to get it into the right mixture to put it onto the fire. Go ahead, Kiri. And then applying the juice. So whether you've got an engine as your primary delivery device, that's one of our recent purchases. Nice 8,000 GPM main deck gun with two 2,500 deck, monitors on the back. So that gets us for our largest tank in that facility. That is our delivery device, all the way up to the picture on the right is a Williams Bigfoot 14,000 GPM monitor on one trailer. So deck guns, portable monitors, trailer mounted monitors, or engineered systems. Go ahead, Gary. So one of the most common engineered systems that we see out in the industry is a semi-fixed system. So you've got foam chambers or foam makers on the side of a tank, and the foam piping runs out either through or over the dike wall, and the foam engine or the trailers can pull up, proportion, and put foam solution into the pipes. It makes its way up to the chamber, gets air put into it, and it flows down the wall of the tank gently into the seal area. Or if it's sized appropriately for full surface and it's an internal floating roof, it may flow across the whole surface of the tank without having to climb the tank or get on the tank and put that foam solution in. Next, you could have a fixed system. So you could have a system that has a water container, it's got the pumps, it's got the foam storage facilities, and then it goes out and automatically through different control valves or different systems can take and put that foam into the areas where you have it, whether it's sprinkler nozzles or foam makers or monitors. A nice engineered system makes that easier. Go ahead. We talked about logistical challenges on hose. Just got a few pictures. As you start lining things up to get all of the water that you need to make sure you think through, how am I going to position the different apparatus? What apparatus do I need to achieve the flows that I have for my facility? And who has them? Where can I get them? Do I have everything that I need? And how am I going to put it down? So when you start laying large hose on the ground and you fill it up with water, it's really difficult to change your mind and move stuff. So you got to have a good plan, and you got to be able to plan through those logistical challenges, hopefully before you have an emergency. Go ahead, Kerry. Some future foam challenges. So Ryan talked a little bit about, do we use foam? We don't use foam. And I can tell you that there's a global discussion going on about the different firefighting foams that we've used in the past and what should we be using into the future. And some of the challenges that we've seen with moving from a fluorine-based or fluorine surfactant-based foam like the AFFFs to a synthetic fluorine-free foam is application rate. It could be application density. And so when I talk about application rate, NFPA 11 talks about a 0.16 gallons of foam solution per square foot of surface area of the tank. Different companies have adjusted application rates depending on size and diameter of tanks. Application density is all about the percentage of concentrate in the foam solution. So am I putting 1%, 3%, 6%, 12%? How do we expand the foam? How do we get enough expansion? Is it expanded, 5-to-1 with air, or 11-to-1, or 15-to-1? Am I using compressed air foam systems where I'm driving a bunch of air into it? Delivery, large over-the-top delivery devices are really challenged for the new generation fluorine-free foams with aggressive plunging into hydrocarbon liquids. And that's that last box on my future foam challenges. Is it oleophobic or oleophilic? So the fluorine surfactants in AFFF were all about fuel shedding and not picking fuel up into the bubble, so that the bubble could lay on top of the surface of the fuel and separate the fuel from the fire and extinguish it. And so when we take a 9,000 gallon a minute monitor and we throw 9,000 gallons a minute of foam solution 300 feet through the air into a tank of burning liquid, that foam will plunge several feet into the liquid level of the tank. With a fluorinated surfactant, the bubbles hit the surface of the liquid, they plunged down, they floated to the top, and didn't pick any fuel up into the foam bubble. Without the fluorine surfactant, some of the new generation foams are more oleophilic, so they like fuel in the bubble. They pull fuel into the bubble. So going over the top with large, heavy streams and deep plunging into the liquid, that first foam that starts to bubble to the top is full of fuel in the bubble. And it makes it really difficult to put the fire out when the foam itself is flammable. So delivery methods and foam are really tied together. We have seen some success with delivery methods that can apply the foam gently to the surface through either foam makers or other ways to let the foam roll down the side of the tank and across the liquid, or if we have a spill in a bund area, to be able to roll the foam across the burning liquid from a non-burning area and let it just move across the surface. So those are some future challenges that the industry is still trying to work out. Go ahead, Carrie. So my last slide, both Ryan and I, with just a few minutes, gave you just a taste of what bulk storage emergencies are all about. There's other places that you can either get more training or more education or send your emergency responders to. And by no means is this an exhaustive list. This is a list that I've had personal experience and participation with. So Texas A&M at the Texas Engineering Extension Service has a bulk storage emergencies pro board class. It's a 3-day class that gets you kind of that basic understanding of bulk storage emergencies and how to deal with them. Also got a 5-day advanced bulk storage emergencies class that they deliver every year during the annual industrial fire school in July. Last fire, that industry consortium, they do storage tank emergency classes around the world. Neil Ramsden is our project coordinator for last fire, and Neil does usually more than one class a year. This year with the pandemic, it's been really tough to get those in. And then vendor schools. Ryan's company, U.S. Fire Pump, they have some great training both at their facilities in Louisiana, at LSU, at Texas A&M, and at people's facilities. Williams Fire and Hazard Controls, another vendor school. Perimeter Solutions, they used to have a really good U.S. training, Hellfighter U. They still have some training with Perimeter in Spain, where their factory is, or primary factory, at Central Jovelinas. So there's lots of places to get more education. And again, this is just to kind of scratch the surface taste of, what do you need to think about if you've got bulk storage facilities with flammable and combustible liquids. Thank you for your time.
Stephen, thanks so much. We've had this conversation before about I'm not usually in the rooms when the presentations are taking place, so having an opportunity to learn something personally different and to understand what it is that you guys do. We certainly see storage tanks here in Houston all over the place, and I'd oftentimes had questions about them, and so I really thank you for your presentation. A couple questions. In one of your prevention slides, you talk about construction standards and managing risk. But is there one standard that provides overall guidance on atmospheric storage tank protection systems?
Cassie, great question. That's one of the challenges I think that terminal operators or storage tank operators and emergency responders have, is there's not a single standard for storage tanks. Whether it's the flammable liquids code in NFPA 30, or NFPA 11 for foam, or 25 for equipment, and then lightning protection, then API standards for construction, API standards for some response to refineries and bulk storage facilities. AFPM has some standards. And then insurance companies like Marsh put out some recommendations to their insured about risk management. But it would be really nice someday if we had one standard that a storage tank operator could go to and say, okay, here's what I need to know about designing and maintaining my storage tank facility.
Okay. Both you and Ryan talked about foam, so that leads me to my second question, is what's industry doing from an end user perspective on supporting new foam development?
So another great question, Cassie. The transition from fluorinated foams to fluorine-free foams is an emerging issue. And typically, as end users, we kind of sit back and we let the manufacturers develop a product and say, okay, I've developed this product for you. Now you should use this. The drive to change for environmental reasons and human health toxicology reasons has really gotten the end user involved in the research and development of the new fluorine-free foams. So me personally, I'm our last fire steering panel member. And so we're doing testing all around the world. We partnered with National Fire Protection Association Research Foundation and the Navy and DOD, and we've done a lot of testing at the Naval Research Labs in Maryland. We've done testing at Southwest Research in Texas, in Budapest, Hungary, in Vernon, France, in Gijón, Spain. So all around the world, it's been a great partnership between manufacturers and end users to try to make sure that we get the performance that we need for the new foams, and that we don't make a regrettable substitution with the environment or human health with new foams as well. So it's a challenging problem or a challenging issue, and both the manufacturing community, the vendor community for emergency response, and the end user community have really partnered well together. And many of our regulators have as well, have been part of that conversation and moving things forward. Great question.
Okay, thanks, Steve. Puts my mind at rest knowing that so much goes into this from a human health standpoint, from an environmental standpoint, from a facility standpoint. So I really thank you for your input today. Well, that wraps it up for us. Thank you for joining. I want to remind you that The full bios are on the replay portal. And also, if you have a question for a speaker, for either Stephen or Ryan, you can communicate with them directly by email. So thank you for joining us today. And that's